In this tutorial, we shall perform a general static analysis on a three-dimensional frame made up of I-beams. Aside from learning to use beam elements, you'll be introduced to important topics, such as the use of connectors as well as constraint equations to represent joints. Let's take a look at a model of the frame. The structure consists of two-dimensional frames which lie parallel to each other. They are connected to each other by horizontal beams at all of their nodes. I shall refer to these as the cross-bracing or cross members, even though they're not in the shape of a cross as the name usually implies. The structure is fixed at the bottom. All the beams on the lower side are constrained in such a way that they cannot translate in the X, Y, or Z direction. However, they are free to rotate. Line loads of 1500, 1000, and 500 newtons are applied as shown in the figure. We are going to use the dimensions from this schematic. We will use SI units, where length is in meters. The beams are made of steel with a density of 7,800 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. Our beams are I-beams. We will use different cross-sectional profiles for the beams in the frame and cross members. Note that the upper and lower flanges of the beams are not of the same length. The purpose of using such a profile in this tutorial is to demonstrate how to orient beams in Abaqus. When setting up the simulation in Abaqus, we will model the beam members using line segments, or more correctly wire features, just like we did in the truss analysis examples. We will then define beam profiles, create beam sections, and assign these profiles to them, and finally assign these beam sections to the wire features. The purpose of this tutorial is not only to work with beam elements, we're also going to introduce you to connectors. Connectors allow you to model a joint or a connection in Abaqus, and you'll see how this is done. In addition, we're going to introduce you to equation constraints by demonstrating how they can be used to create a joint. Here's how we'll set this up. The joints between the members of each frame are weld joints. We won't be specifically creating these because Abaqus assumes the joints between beam elements are weld joints. We will, however, need to define the joints between the frames and the cross-bracing. We will make these pin joints. We will use connectors to define most of them, and equation constraints for the rest, so you'll see how to accomplish the same task using both connectors and equation constraints. Also, in order to use the connectors and equation constraints, the cross-bracing will need to be created as a separate part from the frames. So the two frames will be created as one part, and the cross-bracing as a second part. Beam elements will be used for the analysis. These elements are good for modeling structures in which one of the dimensions, specifically the length, is much greater than the other two. All beam elements in Abaqus allow deformation due to axial loads, bending, and torsion, hence these are ideal for the problem we are simulating. So start up Abaqus and let's do this. Let's start by opening up a new file. We shall rename the model beam frame. Let's create a new part. We'll name this part frame. The modeling space is 3D since it's a three-dimensional frame. The type is deformable. And we're going to set the base feature to point. When we created the barbell stand, we used a solid as the base feature because that was a three-dimensional solid. And for the truss structure, we used wire as the base feature and immediately sketched out the truss using wires. But this time we're going to go with point so that Abaqus can create a reference point for us, and we can use that as a starting point to start drawing out the rest of our beam structure. Essentially, using point helps us to create a part without actually putting anything in it, and then we can work from that point on. And then once we have that part created, we can then create the rest of the beam frame inside of that part container. And we'll set the approximate size to 20. Abaqus prompts you to enter the coordinates of the point. We're going to set it to 0, 0, 0, which is the origin, and then hit the enter key on your keyboard. You notice that Abaqus creates a point which appears in the viewport as an X with the letters RP next to it because it's a reference point. And so we've got a part, but the part is only a reference point, and we can now create the rest of the structure around this reference point. Now our beam frame consists of two frames, two two-dimensional frames connected by a cross bracing. So we're going to start by creating one of those frames. To do this, we're going to use datum points and lay those down in the parts module and then sketch out the frame using those datum points. We need to use the create datum point offset from point tool. This tool might be hidden behind the create datum point enter coordinates tool. So keep your left mouse button pressed down on that, and that should reveal the rest of the create datum point tools. Abaqus prompts you to select a point from which to offset. We click on our reference point, and then type in an offset of 13 meters in the X direction. If the newly created datum point is not visible in your viewport, you can use the Auto Fit View tool. Similarly, we create two more datum points by offsetting from the reference point. Next, we're going to use the Create Datum Plane using 3 Points tool. This will allow us to create a datum plane using the 3 datum points that we've just created, and then we can sketch out the frame on that datum plane. Abaqus prompts you to select the first point, then the second, and then the third. That'll make up the datum plane. We're going to select the 3 points in a counterclockwise direction so that the normal to the plane points out of the screen toward us. And this will help orient the sketch in a way that's easier for us to work with. If you were to select the points in a clockwise direction, the normal to the plane would be flipped, so it would be going into the screen, and that would flip our sketcher when we try to sketch the frame. Once the 3 points have been selected, Abaqus creates the datum plane. You may not see it at first because your viewport's not big enough. Using the Auto Fit View tool should help. Now we need to sketch on this plane, but in order to create a sketch, Abaqus is going to ask us what plane we want to sketch it on, and to also select a datum axis or a line that helps us orient the plane before we sketch on it. You'll understand what I mean in a moment. For now, let's go ahead and create a datum axis. We'll use the Create Datum Axis Principal Axis tool. This allows us to use one of the principal axes, basically the X, Y, or Z axes, to draw a datum line. We'll go with the Y axis. Abaqus goes ahead and draws a datum line on your screen, corresponding to the Y axis. Now it's time to sketch the frame. We're going to use the Create Wire Planar tool. Abaqus prompts you to select a plane for the planar wire, and this is why we created the plane in the first place. So hover your mouse over the edge of the plane, and when it lights up in red, click on it. Next, Abaqus asks you to select an edge or axis that will appear vertical and on the right. We're going to use the drop-down to change it to vertical and on the left. And then we're going to use the datum axis or the datum line that we created just a moment ago. So now you see why we created the datum plane and the datum line. It was basically to give us a surface on which to sketch. Abaqus now puts you in the sketcher view with a grid. We'll use the Create Lines Connected tool to draw our frame. I'm going to zoom in using the scroll wheel of my mouse so I can see the datum points better. Go ahead and sketch the frame. Notice that Abaqus automatically constrains the horizontal line segments with an H, indicating that they're horizontal, and the vertical line segments as vertical. So we don't have to create that constraint on our own. We're going to need to split up some of the line segments to create the individual beam members, and for that we're going to use the split tool. It might be hidden behind the auto trim tool. Next, we're going to use the Add Dimension tool to dimension the frame. We'll use the Add Constraint tool to create equal length constraints for beam members that are of the same length. Once the sketch is complete, you can hit the Done button. Now we're going to create the other frame. Once again, we're going to need to create a datum plane on which to draw that frame. But this time, to create a datum plane, we're going to use the Create Datum Plane Offset from Plane tool, which basically allows us to use our current datum plane to create a new one by offsetting a distance from it. Abaqus prompts you to select the datum plane from which to offset, so go ahead and click on our datum plane. It then asks how we want to specify the offset, so we're going to enter a value. Abaqus draws an arrow on the screen to show you the direction of the offset, but since we're looking at it in 2D, it's a little hard to see which direction this arrow is pointing, whether it's pointing into the screen or out of it. So I'm going to use the Rotate View tool to see it a little better. And once I've rotated it, I'm going to click again on the Rotate View tool to exit out of it. If the arrow is pointing in the opposite direction from which we wanted to offset the plane, we would click the flip button and that would make the arrow point into the screen. Click on OK, and then we're going to give it an offset of 1.5 meters. Abaqus creates a new datum plane, offset 1.5 meters from the old datum plane. Once again, we're going to create the datum points using the Create Datum Point Enter Coordinates tool. Notice that the x and y coordinates of these datum points are the same as the previously created ones, but the z coordinate is 1.5, which creates the new datum points on our new datum plane. Again, we'll use the Create Wire Planar tool to sketch the frame. We'll select the new datum plane, and for the edge or axis that appears vertical and on the left, we're going to use our originally created datum line. It's going to be hard to see our new frame sketch over the old one, so I'm going to rotate the view a little bit. Now we'll use the Create Lines Connected tool to draw the frame. We'll dimension it using the Add Dimension tool. And we'll use the Split tool to split the line segments up into individual beam members. We'll also use the equal length constraint as required. Click the Done button to exit the sketcher. We now have the two frames. Notice that both the left and the right frame were created as the same part. Next, we're going to create the cross bracing as a separate part. Once again, we'll go with a 3D deformable part with a point as the base feature. We set the coordinates of the point to the origin, and Abaqus goes ahead and creates a reference point. We'll create the nodes of the cross bracing using the Create Datum Point Enter Coordinates tool. Type in the coordinates for the datum points. I've got them typed out in a notepad file, so I can easily copy and paste from that. Once we've got all the datum points created, we can use the AutoFit View tool to see them a little better. To create the cross braces, we're going to use the Create Wire Point-to-Point tool. In the Create Wire feature window, we're going to set the Add method to disjoint wires as opposed to chained wires, which is selected by default. This is because our cross-brace members are not connected to each other. Click the Add button to create the first wire. Abaqus asks you to select the first point. You might have to use the Rotate View tool so you can tell which points are on which frame. Abaqus prompts you to select the first point and then the second one, and it then creates a wire feature connecting them. Continue the process to create the other cross-brace members. Once you've created all the members, click the Done button. You see that Abaqus has populated a table with the first and second point of each wire feature. At a later stage, we're going to want to select all of these wire features as one block, so it makes sense to go ahead and create a set at this stage by checking off the Create Set of Wires option. I'm going to go ahead and save my work at this point. Next, we're going to create the material. The material is steel with a density of 7,872 kilograms per meter cubed. It has a Young's modulus of 200 gigapascals and a Poisson's ratio of 0.29. Now when you use beam elements in Abaqus, it's not enough to just define the start and end nodes. You also need to define the cross-sectional profile. So double-click on the profile item in the model tree. You see the Create Profile window. We're going to name our profile Frame Profile, and we're going to choose I as the shape, since our beams are going to be I-beams. When you click Continue, Abaqus shows you the Edit Profile window. Here we can enter in the exact dimensions of the I-beam profile. Type in the cross-section profile dimensions of the beams that make up the frames. Now we're going to create the profiles for the cross-brace beam members. We're going to name this profile Cross Profile. Now it's time to create sections. We're going to create two sections, one for the frames and one for the cross-bracing. We're going to call the section for the frame section. We'll set the category to beam and the type to beam as well. You see the Edit Beam Section window. When creating a beam section, Abaqus asks you whether to perform the section integration during the analysis or before it. If you choose during analysis, you request Abaqus to calculate or integrate the section engineering properties or the cross-sectional behavior from section integration points during the analysis. This basically means that the section properties must be recomputed as the beam deforms over the course of the analysis. And this includes properties such as cross-sectional area, moments of inertia, and so on. The material behavior is also calculated at each point on the section during the analysis as the beam is deforming. This works for linear behavior and also for nonlinear conditions where the nonlinearity is a result of material nonlinearity. On the other hand, if you were to choose before analysis, the cross-section properties would be pre-computed at the beginning of the analysis. And then you would need to provide section properties such as Young's modulus and shear modulus and section Poisson's ratio. And that would be useful for a linear analysis or for a nonlinear analysis where the nonlinearity is also caused by other factors other than the material nonlinearity. So we're going to go with during analysis. You'll also notice that Abaqus expects you to give it a profile for a beam section. For the frame section, we're going to select the frame profile that we just created. We'll leave everything else set to the defaults and click OK. We can repeat the procedure to create the section for the cross bracing. Now that we've created the sections, the next step is to assign these to the parts themselves. I should point out at this stage that beam sections, such as the ones we just created, can only be assigned to wire regions. Now that works for us because the parts we created were made using wire features. If you recall, we used the create wire planar and the create wire point-to-point tools when creating the frame and when creating the cross bracing. We're going to expand out the cross bracing part and double click on section assignments. We select all the cross brace elements and assign to them the section we called cross section. Repeat the procedure for the frame part. Another very important thing I should mention when dealing with beam sections is that beam sections must be assigned orientations. Basically, Abaqus needs to know which way the eye profile of our beam is oriented. So for example, it could be on its side, in which case it would look like an H. So we need to orient it so that it is an eye. And in fact, the two flanges of our I-beam are not the same dimensions. So we need to let Abaqus know if the shorter flange is on the top or the longer one, and so on. And in our case, we want the shorter flange on the top and the longer one at the bottom. The shorter one was 0.08 meters and the longer one was 0.11 meters, if you recall. So let's go ahead and assign beam section orientations. I'm going to start with the cross bracing. So we want to display the cross bracing on the viewport. You can do this by double clicking cross bracing in the model tree as you've done many times before, or you could set the module to property using the drop-down, the model to beam frame, and the part to cross bracing, and that'll display the cross bracing in your viewport. Go to the Assign menu and choose Beam Section Orientation. Abaqus prompts you to select the regions to be assigned the beam section orientation. So we're going to select all the members of the cross bracing, as all their profiles are oriented in the same manner. Abaqus then asks us to enter an approximate N1 direction. The N1 direction is the direction in which the 1 axis or the x-axis of the profile should be pointing. And the tangent vectors displayed in the viewport in red are basically going to be normal to the cross-section profile. Also, the cross-section is going to be sort of extruded out in the direction of those arrows. So in our case, if the normals to the cross-section profile are pointing out from the screen toward us, we would like the x-axis or the y-axis of the profile to be pointing toward the right. Therefore, we're going to enter in 1 as the x-coordinate and 0 as the y and z coordinates for the n1 direction. Hit enter on your keyboard, and you see Abaqus draws the orientations in the viewport. You need to click OK to confirm the input. Just to make sure we've got them oriented correctly, we can tell Abaqus to show us the beam profiles in the viewport. We use the View menu and click on Part Display Options. In the Parts Display Options window, check off Render Beam Profiles and click OK. You see Abaqus has rendered the beam profiles in the viewport, so we can see they're oriented just the way we'd like them to be, with the eye standing upright in the vertical direction, and the shorter flange on the top and the longer one below. Now let's assign beam section orientations to the frame. Switch to the frame part by choosing Frame from the Part drop-down. Once again, choose Beam Section Orientation from the Assign menu, and select the entire frame when prompted to do so. This time we're going to tell Abaqus that the y-axis or the x-axis of our profile points outward along the z-axis toward us. And click OK to confirm the input. You probably noticed that the arrows at the top and bottom of the frame did not point in the same direction. So this means our I-beam profiles are flipped on the top and the bottom. So we've got an upside down eye for the bottom one. Now I went with this just to make this tutorial a little easier, but if you'd wanted the beams to be the same orientation on the top and bottom of the frame, you would have to select the beam elements on the top and bottom separately when assigning the beam profiles, whereas we just selected the entire frame at one time and assigned a common N1 for the entire thing. We can then turn off beam profile rendering by going to Part Display Options in the View menu and unchecking the option. Now let's create the assembly. We can instance both the frame and the cross bracing as dependent instance types, which means that we'll later create the mesh on the parts themselves. Now if you want to render the beam profiles in the assembly module, you once again go to the View menu, and you notice that Part Display Options has been changed to Assembly Display Options, so click on that. Check Render Beam Profiles, and click Apply. We're going to uncheck the option and click Apply again to remove beam profile rendering. Now that we've got the frame and the cross bracing assembled, we need to specify what kind of joints exist between the cross brace members and the frames. But before that, let's talk about the joints in the frames themselves. When we created trusses in the truss tutorials, the nodes of the trusses were pin joints by default, because when you use truss elements in Abaqus, the nodes of the trusses are automatically treated as pin joints by Abaqus. Beam elements, on the other hand, are different, and the nodes between the beams are treated as welds. In a weld, the nodes are basically fused together, so you're going to see transfer of both displacements as well as moments, whereas in a pin joint, there's going to be no transfer of moments. Now we would like the joints between the cross bracing and the frame to be pin joints. That means they can transfer displacement, but not moments. We're going to explore two methods of doing this. The first one involves using connectors, more specifically joint connectors, and the second one involves using constraints, or equation constraints. We'll use connectors for the majority of the joints, and we'll use constraint equations for the rest of them. Let's switch to the interaction module by using the module drop-down menu. What we're going to do is create wire features connecting the cross brace to the frame at each of the joints. And we're going to assign all of these wires to a set. Then we're going to create a connector section and assign it to the set of wires using the connector assignments item. Let me demonstrate. Click on the Create Wire Feature tool. Now this gives you a window similar to the one you saw using the Create Wire Point-to-Point tool when you created the cross bracing. Once again, we're going to choose Disjoint Wires, and then we'll click the Add button to actually add the wires. Below the viewport, Abaqus prompts you to select the first point, so click on the first node. It then asks you to select the second point. Now needless to say, our nodes are going to be one above the other since the cross brace meets the frame at that node. So we've got one node on the cross member and one node on the frame. And it's a little hard to see both the nodes. In fact, it's practically impossible to see them. But you don't need to worry about that because the second time you click on it, it's going to choose the node that wasn't selected the first time. We'll repeat the procedure for all the nodes except the ones that we're going to do using the constraint equations. Click the Done button. You see that Abaqus has created a table with point 1 and 2 for each of the wires. Make sure you check off the option Create Set of Wires. This will make it easier for us to assign a connector section to these wires. You notice that Abaqus has created a set of these wires in the Sets item and has given it its own name, which is Wire1 Set 1. I'm going to rename this, so right-click on it and choose Rename. We'll change the name to Set of Connector Wires. Now let's create the connector sections. Double-click Connector Sections in the model tree. You see the Create Connector Section window. Let's name our connector Frame Cross Connector Section. Now you see a few different connection categories. There's Assembled Complex, which will give you a few predefined connection types, such as a hinge or a weld. Then there's Basic, which allows you to specify things like rotation and translation, and that's the one we're going to be using. And the third one is MPC, which is multi-point constraint. And these allow you to have constraints between different degrees of freedom of the model. And they can be nonlinear. For example, an MPC of type beam for two nodes would basically constrain the displacement and rotation of the nodes as if there was a rigid beam between them. And you can also use user subroutine MPCs if you went with that option. We're going to go with basic. We'll set the translation type to join. This means that displacements will be transferred between the frame and the cross bracing. So if the cross bracing gets displaced a little way, the frame will also get displaced at the node and remain connected to it. On the other hand, we'll set the rotational type to none so that the cross bracing can rotate freely without affecting the frame, so there's no transfer of moments. Abaqus shows you the available CORM, where CORM is components of relative motion, as well as the constrained ones. So what it's telling us is that we've now constrained U1, U2, and U3. And that, as you know, is a pin joint. And you can click the Show button for a visual representation of this if you like. Then click Continue. We get the Edit Connector section window. We're going to leave everything here at the defaults. Now that we've created the connector section, we need to assign it to the connector wires we created before. So expand out the assembly item in the model tree and double-click on connector assignments. Abaqus prompts you to select the wires or attachment lines to be assigned the section. Now in our case, we'd gone ahead and created a set of all the connector wires, and this is why we did it, so that it would be easier for us to select those wires at this step. So we're going to click on the Sets button, and in the region selection window, we'll click on Set of Connector Wires. If you like, you can check off Highlight Selection and Viewport so you can see them better. And once you're satisfied, click on Continue. Next, Abaqus wants you to select the section that you wish to assign to these wires. Since we've only created the one section, it's the only one available in the drop-down list. So select it and click OK. So now we've created pin joints at most of the nodes where the cross-bracing connects to the frames. For the remaining nodes, we're going to use equation constraints. In order to do this, it's going to help if we assign those nodes on the cross members as well as the frame to sets, so it's easier to select the one we want. Expand out the instances container in the assembly container. Right-click on frame 1 and choose suppress. This suppresses the frame 1 instance, and you only see the cross-bracing now. Now it's going to be easier for us to select the nodes on the cross members and assign them to sets. Double-click on the sets item. We're going to call our first set cross node 1 and select it from the viewport. Repeat the procedure for cross node 2. Now let's unsuppress the frame and suppress the cross-bracing. Now you see only the frames. Let's create frame node 1 and frame node 2. Remember to unsuppress the cross-bracing once you're done. Now that we've created the sets, let's add constraints. Double-click the constraints item in the model tree. Now we're going to use equation constraints, so let's talk about how these work. You basically write out the constraints in the form of an equation that looks like a1u1 plus a2u2 plus a3u3 and so on equals 0, where a1, a2, a3, basically all the a's, are coefficients, and all the u's are displacements of specific nodes. So for example, to constrain cross node 1 and frame node 1 in the x direction, we're going to say 1 times the displacement of cross node 1 in the x direction minus 1 times the displacement of frame node 1 in the x direction equals 0. And that would constrain the node in the x direction. We'd repeat the procedure for the y and z nodes, and then we'd repeat the entire thing for cross node 2 and frame node 2. So basically in the end you should have 6 equations. In the create constraint window, let's set the name to join constraint 1 and choose equation from the type. Click continue. In the edit constraint window, our first coefficient, or a1, is 1, and the set name is cross node 1. And this equation is dealing with constraints in the x direction, so we're going to set the DOF, or degree of freedom, to 1. We're going to set a2 to -1, and the set to frame node 1 with the same degree of freedom, because that's also for the equation in the x direction. So what this represents is 1 times the displacement of the set cross node 1 in the x direction minus 1 times the displacement of the set frame node 1 in the x direction should equal 0. Or put in simpler terms, the displacement of cross node 1 equals the displacement of frame node 1 in the x direction. We'll repeat the procedure for the y direction. We'll call it join constraint 2, and this time we'll set DOF to 2, indicating it's for the equation in the y direction. And then repeat the procedure for the z direction. We then create the equation constraints for the other node, which is cross node 2 and frame node 2, in the x, y, and z directions. So in the end, you should have joint constraints 1 through 6. Now that all the joints have been created, let's move on to the steps. We're going to create a step called apply loads, which is a static general step, and insert it after the initial step. Now let's create the load. Double-click the loads item in the model tree. We're going to call it crossLoad1. It's going to act in the apply load step. It's a mechanical load, and it's of type line load. Now line load basically makes a force per unit length act on a beam. Abaqus still thinks you're selecting sets, so click on Select in Viewport to allow yourself to select the beam member in the viewport. Select the beam member and apply a load of 1000 newtons in the negative y direction. Similarly, apply loads for the other 3 beam members. Let's create the boundary conditions. Double-click the BC's item. We're going to call it fixed bottom and apply it in the initial step. For the type, choose displacement/rotation. For the region, select all the beam members at the bottom of the structure. We're going to check off U1, U2, and U3 so the beams at the bottom of the structure cannot translate in any direction. However, they're free to rotate about any axis. You might have noticed that we did not apply equation constraints to two of the nodes at the bottom. We only used the equation constraints for the two nodes at the top of the structure, because if we'd used equation constraints at the bottom and then used the boundary conditions we just did, we would have basically over-constrained the structure, and this would have given us an error. Now let's mesh the structure. We'll start by meshing the cross-bracing. We'll assign it an element type B31, which is a two-node linear beam in space. And we'll seed the edges by number, assigning 4 elements to each beam of the cross-bracing. We'll do the same thing for the frame. Now that the parts are meshed, let's create the job and run it. There appears to be an error. It reads, the following connector assignments reference regions which are empty, or have been deleted or suppressed. So it's possible we've deleted or suppressed something we earlier created by mistake. It refers to section assignments to the frame cross-connector section. So let's take a look in the assembly container. Maybe it's in the sets item or in the features item. And here we see it. It looks like this feature has been suppressed, either by a mistake on my part or at some point during the setup, Abaqus for some reason decided to suppress it. But we're just going to unsuppress it and continue on with our analysis. Once the analysis finishes running, we can right-click on the job and choose results. And I'm going to plot the deformed shape just to make sure the analysis did actually run as expected. Of course, there's no way the frame's going to deform to the extent you see in the viewport. Abaqus has gone ahead and multiplied the deflection by some factor to make it more visible to someone looking at this. But if you went into the common options and changed the scale factor to 1, you probably wouldn't be able to see any deflection at all. This tutorial's been pretty heavy on other content, so we're not going to spend any time post-processing. Hopefully you've got a good idea of how you analyze beam structures, and you've also learned a thing or two about connectors and equation constraints.